Hey guys, this is Saptarshi here, and I welcome you on a video tutorial on tSNE. Okay, so it is a state-of-the-art dimensionality reduction technique. tSNE stands for T-distributed stochastic neighborhood embedding. I am sure the first reaction is not going to be very pleasant for you when you hear the full name. Okay, but please bear with us. We will try to make it as simple as possible. So let's set some context. Let's say that we have some data points in high dimensional plane. So you know already that in case of text or image, bioinformatics, recommendation system, individual observations has more than 10,000 features, 1,000 features, 1 lakh features, okay? And you want to find some patterns or structures in the data. So it is not at all trivial, okay? So one of the things that can be done is that reduce these 10,000 features to 2 or 3 features and then draw them in a scatter plot, okay? And we can definitely find some pattern in that case. So PCA and LDA tries to reduce dimension, and how it tries to do is PCA tries to find new features such that they are linear combination of original features which explains maximum variability in the data. LDA tries to ensure maximum separability among classes. So it is a supervised technique and needs the class levels. Okay. tSNE takes a different view. So let's try to understand that with a diagram. So let's say, these are the points in high dimension. So as in high dimension, it is very difficult to visualize. So we have plotted in 2 dimension only. Assume that it is in high dimension. And we want to plot it into lower dimension such that the locality or the neighborhood structure is preserved. So what do we mean by this? We mean that if this point is the nearest point or nearest neighbor in high dimension, this should be preserved when we take this to low dimension or a 2-dimension plane. Okay, and this is not only true for this point, this should be true for all other points. Okay, all right. So if you look at this particular representation, you can understand that this doesn't qualify or this doesn't have such a characteristics. However, if you look at a data like this, this actually preserves the neighborhood structure or the neighborhood information. Okay, so this technique, one of the brains behind this technique was Geoffrey Hinton, who is also the founding father of deep learning and many other theories. So this paper, the original paper, the first paper was named as tSNE, okay, stochastic neighborhood embedding. So this is what we are going to study first, and then it was extended to something called as tSNE, okay, and this was published in JMLR, Journal of Machine Learning Research, as I mentioned earlier, also one of the top journals of machine learning. This particular paper itself has got more than 12.5k citations. Okay, so highly recommended to read. All right, so now let's understand this global versus local variability. So as I said that tSNE tries to preserve the local neighborhood structure. So what PCA tried to do? PCA tried to maintain the overall variability of the data. Okay, and I'm sure you will agree that the overall variability can be best represented or most easily represented by the variance of the data, right? And if I think of the variance is nothing but the squared distance from the mean. The farthest points actually contributes most to the variance, right? So they have the highest distance with the mean, right? Okay. So we can say that PCA tries to maintain the large pairwise distances. Okay. So this is why, we will say that PCA has a global focus. Okay. So it is looking at distances or trying to preserve those distances which are far from each other. All right. From 2000, actually people started focusing on local methods. They thought that this large pairwise distances, which are global distances, may not be the best way to represent that particular data set. okay, and that may not be very stable as well. So they started focusing on local methods. Couple of local methods are isomap and LLE. Okay, so LLE stands for linear local embedding. So both came around the year 2000. So isomap had a problem of slower convergence. Okay, whereas LLE had a problem of collision. So what do you mean by collision? So as we move from higher dimension to lower dimension, it may so happen that several points of higher dimension gets converted to the same point in lower dimension. So that would be called as collision. All right. So now this was one of the issues of PCA, that it focused on global learning. Another problem was that it didn't understand manifold learning. So what is manifold learning? So manifold learning is best illustrated by this Swiss rule. Okay, so this you can understand that the points which are in the same curvature, okay, they are similar. Okay, so that has been color coded similarly, appropriately. So if you apply PCA and then in this reduced dimension you plot them by the original colors, you say that it has gone all over the places. Okay, so this separability is no longer maintained. Okay, so there is a concept, and this happens because PCA focuses on Euclidean distance. Okay, so what is Euclidean distance? So Euclidean distance is actually, if you look at these 2 points, okay, so they have small Euclidean distance. Similarly, here also there can be small Euclidean distance, though they are from completely different curvatures. So instead of Euclidean distance, if you consider geodesic distances, so this will be appropriately stretched out, so that points from different curvatures, okay, different curvature equations will be farther from each other. All right. So with this knowledge, now let's look at, or let's try to understand that how we can try to represent this neighborhood information. So let's take a simple example. Let's assume that this is in higher dimension, okay, and these are, let's say, 9 points that are there. So this is your reference point, okay, this is your reference point, and what I want to do is I want to represent this point, okay, in terms of its neighbors. All right. So how can I do that? So what I can do is I can first look at the probability of picking this neighbor. Okay. So let's say this neighbor has been picked for lower dimension. So if this neighbor has been picked, what is the probability of this neighbor being picked? Okay. And you will agree that this should be an inverse function of the distance. One such function is this exponential function, and if you use this exponential function, okay, this is similar, this has similar characteristics with a Gaussian distribution. So you can think of that this point, around this point there is a Gaussian distribution, okay, and what happens is that as you go farther away, so for these points, okay, the probability of picking these up will be very close to 0. All right. So this can be seen as that these were the distances. If this is a reference point, the distances are 1, 2, 2 and 3 respectively. So if you apply this function on the distance, okay, so you get a value like this. All right. And if you convert, so if you find the probability using this formula, okay, you get a probability like this. So you see that the one that was the closest has the highest probability, and then the probabilities has reduced further. All right. So you see that earlier, this was a vector in 100 dimension. Now this can be thought as a probability distribution. What this probability distribution actually represents? The probability distribution represents the probability of picking its neighbors given that this has been already chosen. Okay. So as I said, the data matrix can be converted to a probability distribution. All right. So now let's say that we have some means, okay, some magic trick by which from the original 100 dimension or 1000 dimension plane, we are able to go to a 2 dimension plane. Okay. And in this two-dimension plane, we represent the points as y1, y2, yn, like this. All right. And let's assume that we had k neighbors, okay, based on the Gaussian function. So we can think this to be a probability distribution. So the example that we discussed, instead of that 100 a vector with 100 features, I can represent it as a probability distribution. And let's call this as P. All right. So for n observations, we have n such probability distributions. Okay. And in same manner, let's compute this probability distribution of each of the points in Y. Okay. So we are doing the same thing what we did in the original dimension. We are picking the same point or the representation, lower dimension representation of the same point, and then we are trying to pick up the neighbor and calculating the probability. Okay. And we are using the same Gaussian formula. Okay. Now we have another probability distribution. So we have one probability distribution corresponding to the original feature space, which we are calling as P, and this we are calling as Q. Let's sync this further. Okay. So let's say that we have 10,000 observations of 100 attributes and we are considering 20 neighbors. Okay. And so now P is a collection of 10,000 discrete probability distributions. So for each point you have a discrete distribution and each of them has 20 values because you are considering 20 neighbors. And as we said that let's by some magic or trick, we have converted into two dimension. Now also we have a probability distribution. These two probability distribution, dimension wise at least, are of same nature, right? So both are collection of 10,000 probability distribution, and individual distributions has 20 values each. So can you tell me that what should be the relationship between P and Q? Okay. So we can think about similarity between P and Q. So we have seen that how we can measure similarity between two vectors, but we have not seen that how we can measure similarity between two probability distributions. So let's have some intuitions. So let's say that I have in my original feature space, I am looking at one point, let's say I, and my k is 5, and I have a probability distribution like this. When I have taken this to a lower dimension, okay, so this is one possible representation in one lower dimension, and in another lower dimension, this is another representation. Okay, so what we want. Okay, so let's try to first represent this in terms of a table, and also this in terms of a table. So first what we do is let's find a ratio between the first neighbor of both these probability distribution. Okay, so 0.6 by 0.2 I get a 3, 0.15 by 0.2 I get 0.75, that way. Okay, and similarly let's do the same for this probability distribution. And if I do the same calculation, you will see that the value here is 4.08. And if you run several examples, you will see that if the probability structures are similar, then this sum of these ratios will be lower. So if I use a function of this sum of ratios, okay, so that can work as a similarity measure between probabilities. So this is formalized in a very popular measure called as KL divergence. Okay, so which is a function of this px by qx, which we discussed. Then we are taking a log and also multiplying by the probability in the original feature space. So this is about 1 point. Okay, so when we calculate about all the 10,000 points, we represent that as C, and here your I is 10,000. Okay, so of course you want to minimize the value of C. All right. So now let us look at this particular function. Okay, and let's see that how this is good for preserving the locality or preserving the neighborhood information. So let us take two cases. So always you want this ratio to be small. Okay, so you want either this to be similar, or you want px to be small and qx to be high. So let's take a case where p is large and q is small. So what does that mean? So p is large means that in your original feature space, this was a quite close neighbor. However, q is small. That means that in lower feature space, you could not preserve that information. So this ratio will be high. So that means that c will be higher. So you want to minimize c, so it will result in a big penalty. So whenever it tries to find this q, it will always try to keep this ratio small. However, let's take the other case that q is large and p is small. So in original dimension, they were far apart, but in the lower dimension, they are quite close enough. Okay. So this simply doesn't care much about that. So that's why we say that, it can preserve locality and it ignores global information. Okay. And for finding such a lower dimension distribution, we again use gradient descent, one of our master keys, as we have discussed in one of the previous lectures. So we have discussed only the mathematical intuitions, so we are not going into how we'll solve using gradient descent. Alright. Now there is something called as a perplexity. So we talked about, if you remember, that selecting some neighbors. Okay. So how to select some neighbors? So actually, we talked about distances, and we did not go into discussion that what this distance actually look like. Okay. So it may not be your Euclidean distance. One of the popular choices is a distance like this, okay, which is called as kind of a scaled Euclidean distance, which is divided by the variance. All right. Okay. So if you have a distance like this actually works as kind of a setting of a neighborhood. Okay, so this perplexity actually determines how many neighbors will be considered. Okay, and that way it can balance between local and global, right? So if you have small number of neighbors, you are local, and if you have taken a lot of neighbors, then you are slowly going to the global structure. All right. So in the original paper, the authors have mentioned you should have a perplexity between 5 to 50. So let's look at some example. So let's say that in original dimension. So again, for simplicity, we are even taking the original dimension also in 2D. So these were two set of distributions. So you can see that they come from different Gaussian distributions. Okay. So if you have a low perplexity, this is what the representation in 2 dimension. Okay. So what do you see? So actually it has focused a lot on the local structures. Okay. So it might have looked at some structure like this or some structure like this. Okay. And this is how the lower dimension representation looks like. If you go to a perplexity of 5, this has now nicely identified the structure. Okay. And if you increase the perplexity beyond certain point, okay, so this is just as an illustration. So here we have taken a perplexity which is even more than the number of points that are there, okay, in this example. So this can again become quite random. Okay. So the perplexity should be not very small and not very high. Okay. Now let us try to understand. So this was all about stochastic neighborhood embedding. Okay. Now let us try to understand that what was the motivation between tSNE. Okay. So this was the probability distribution that we were using in the lower dimension, right? So as I said that this follows kind of a Gaussian distribution. This was in SNE. In tSNE, a different formula is used. The formula is something like this. Okay. And actually, as this representation, this represents normal distribution, this actually represents student's t distribution with a degree of freedom 1. Okay. So that's why, as tSNE in the lower dimension follows this probability distribution, okay, you call this as tSNE. Now, an obvious question that should come to your mind is that why do you follow t distribution? So let's try to tell that. So of course, you want to preserve local distance, okay? And while you are preserving local distance, okay, so you also want to do something else. So let's look at this example, right? So what are the local distances? So you see that, this can be considered as local distance, okay? So this is in 2D plane and this is the farthest distance. So this I call as a global distance, okay? To simplify, right? So these two pairwise distances represents local distance and this represents global distance. So now if I want to represent it in a 1D plane so that this local distance is preserved, what can be a representation is something like this. Okay, so you can see easily that both the local distances are preserved. However, what has happened to this maximum distance? So this maximum distance has actually increased. Okay, so when I am trying to preserve local distance, what I want is, I want the large pairwise distances to go farther apart. So from the high dimension representation, when we go to a low dimension representation, we want these to go farther apart. Okay, and actually, that if you follow the normal distribution, okay, so as you go towards the tail, okay, the probability becomes quite small, right? So that means that as the distance from the reference point to the neighbor increases, the probability also goes down. And in case of t distribution, if you remember that t has a farther strong tail. So t distribution looks something like this. Okay. So to get a similar probability here, so what can be, in normal distribution, okay, getting a very small probability, if you had to go to a distance of 10, in t distribution, you will have to go to a distance of 30, right? So this will help us to actually, put more weight to this large pairwise distances. Okay, so that actually motivated the authors to move from SNE to tSNE. Now let us look at a visualization, okay, with PCA and tSNE. So this is on the famous MNIST data set, okay. So these are the two first PCA dimensions and the classes are marked in same color. So you see that, and you remember that MNIST is about 10 digits, right? So from 0 to 10, okay, from 0 to 9, okay, and these are represented by different colors, all right? So PCA, you see that they have gone all over places, only some of them, maybe one it could have, it had identified clearly, whereas tSNE has beautifully separated them out, right? So please remember, both of them are unsupervised, only the color information has been used to color code them, not for anything else, okay? So, this brings to end of our tSNE lecture. I hope we could give you an intuitive understanding of this complicated method, okay? So if you have further question, please feel free to give in the comment section. Thank you so much for watching, guys. Please like and subscribe if you find it helpful.